Good afternoon, everyone. Let's get seated and let's start. I will first go a little bit over the upcoming deadline. So you have all submitted your intermediate reports, and I will work through them this week and hopefully get to you by the end of this Friday. That's my plan, at least. So in terms of homework, you have two homeworks that are already available on Canvas. One is on the regression, the other one is on dimensionality reduction. That includes what we have done in the past week, SVD and random projection. In terms of the project, then you will have your final reports due on April 12th. So have that in mind. And after I grade all the intermediate project reports next Monday, I will go a little bit over what is expected there, but it's already written in this web page, so you can check it out if you are already kind of eager to start working on that, which would be great. And the way we are going to present your works is not through presentations in this lecture, but we'll have a poster presentation in front of the front desk in MEB. So there is a little bit of logistics here in terms of you giving your poster outline, we checking whether everything is fine and giving you like final thumbs up. And here we need to be really on time because then we need to do a huge batch of printing of these posters. So yeah, we will go into that a little bit more later, but just so know that on the instead of the lecture on the 24th of April, we'll have this poster presentation. And then the final homework is going to be during that final week of the lectures, and it's going to be on graphs. Any questions in terms of the upcoming deadlines? Yeah, please.
This is not about the upcoming deadlines, but so the final exam date is May 3rd, right?
I think so.
Have anything due after that? Any presentations? Or...
No, that's the final thing. Yeah.
Okay, nothing after that.
No rows will magically appear here, I promise. Yeah, final exam is going to be the final thing. Yeah. Any other questions? Okay, looks good. All righty, so let's go back into our lecture from the last time. So last time we started to talk about the random projection, and I will just remind you of the motivation for this problem. So we have introduced this in a setting where we have a very large number of features. So the number of columns we have in our data metrics is very, very large. So time complexity becomes an issue if you would like to use SVD when we have large number of feature D, because we know that SVD is not really efficient in the number of features. And in terms of what kind of problems fit that criterion, there are many of them. As I mentioned last time, you can have some kind of gene expression data where each column is some gene, and you might have thousands of them. You might work with images. We have seen one example when I tried to show you best rank K approximation of an image with a cat, and there we had as a number of columns 3,000 pixels. Then if you deal with videos are just a sequence of images, and each image is then, as we have seen, contains lots of columns with pixels. Videos become even more expensive in terms of the number of features we have, the number of pixels. With text data, we would typically have in more traditional techniques where we work with unigrams and n-grams, such as taking TF-IDF scores to produce a term document matrix, like you will have in your homework. There we have maybe dozens of thousands of words in the vocabulary, and therefore the columns in our document term matrix will have dozens of thousands of features. Financial metrics, maybe you are having some kind of measurements of stocks and you measure that over time. You will have a bunch of those because depending on how large the period of time you are taking, climate data also can have measurements of atmospheric oceanic conditions, again, over time. Anytime you have any kind of time series, that time series will likely be very long, and that will cause to have a large number of features. So that was one motivation for our random projection. And I also said that we want to, in some setups, maybe preserve the distance between each point. And that's what random projection gave us compared to other approaches we have seen to dimensionality reduction, where we didn't get a guarantee that the distance between each point will be preserved in our low dimensional representation. Why you care about preserving the distances? Maybe you care only about the similarity of the objects you have, and then the distance is the measure of how dissimilar two things are, which we know that we can kind of connect to similarity. And you don't care about the actual structure of the data. You don't care that if you plot now this lower dimensional representation to see the same clusters that exist in the original data. And now thinking, what kind of data preserves similarity, but clusters kind of fall apart? I actually couldn't think of that example. I think something like if you think about points on the sphere and projecting this to the lower dimensional space might show you that you can preserve distance on a line, but have no clusters anymore. But I couldn't come up with anything concrete. So definitely a point for you also to think about what kind of problems when we project them and preserve similarity might kind of disrupt the structure in the data. And by structure, think about something you can see visually. Like with PCA, if we plot PCA representation of our data, we will still see those blobs that represent clusters. Okay, so this was our setup for introducing random projection. And then we have introduced it, and we have first introduced the lemma that kind of guarantees that a certain number of low dimension of the low dimensional space, we can produce a mapping that will guarantee that we will preserve the distance between each point. I didn't show the lemma again, but that's what it said. And all we need to do is have some unit vectors in k random d-dimensional unit vectors. So these k random vectors are going to make a basis for our d-dimensional space. I'll put a period here. All right. So, okay, let's maybe go over the algorithm again. We have our data matrix where each row is a data point of the size d. So let's say we have here, I don't know, maybe pixels of, and we have d of them. And then we had said, okay, we are going to construct k random d-dimensional unit vectors. Unit means that their norm is equal to 1. And then for every one of these rows in our data matrix, which represents one data point, we said we are going to take each one of these unit vectors, and we are going to make a dot product of our vector with that unit vector. And that will give us value q, which we will put, and we are going to put each one of these k new scalar products into a vector. And that's going to represent our low dimensional representation of the original point. So the point was originally in a d-dimensional space, and now it lives in a k-dimensional space. And then again, I will just repeat it. The big point that we have made is that the distance for every ij, the distance between ai minus aj, so I'll take some north here, it is approximately the same as the distance mu ai minus mu ij. So the distance, we mapped everything to lower dimensional space, but distances are preserved. That was important. And I kind of said that, to me at least, this is actually kind of incredible that you just can take any k random vectors and be able to find this mapping that preserves these distances. And then we have talked about how this is unique to the very high dimensional spaces, because in very, very high dimensional spaces, if we randomly choose two vectors that have two random unit vectors, if we take their dot product, they will the very high probability have a dot product that's very, very low, very close to zero. So we can say that almost orthogonal to each other, because if they were orthogonal, their dot product would be exactly zero. Yeah.
That makes me think, why didn't you just sample them like evenly spaced, like just like enforce it there, like actually, like almost like more than just random?
Because random sampling is the cheapest operation we can have, right? So for orthogonality, we have learned that great, we can find orthogonal vectors if we do SVD decomposition of our space. And then we get those matrices U and V, and those matrices U and V can form a basis. But that operation was expensive. And now we are looking for cheaper options. Randomly drawing vectors is the easiest thing we can do. So it's really time efficient. And of course, if you had chosen orthogonal vectors here instead of just unit vectors, you will probably get better of everything. Remember, we don't have exactly equals to here, so there is still room for improvement. And that's something we are going to play around a little bit with in your homework, where you will see how these how much error you get for different values of your K, because remember that was also important under the lemma we were looking at. Okay, all right, and see here that we kind of got this. So I said we have data metrics, but imagine that I didn't write that we have data metrics, but instead of our data comes into a stream here. The certain data point doesn't depend on the previous data points in this computation, because we are just taking the dot products with these K unit vectors here, which means that you can just take this data in a stream and still find a low dimensional embedding for each one of your data points, meaning you don't need to really store your data matrix A here, which is also nice depending on the problem you might be having. We have also written this in a more compact form by having just a matrix product. So here we are avoiding those for loops, and instead we have our mapping of the entire matrix, meaning the mapping of each one of our points in each row, just to be a matrix product between the data matrix A and a matrix U that we have constructed by putting each one of our vectors into a column. So this is just a more compact way of writing the same thing we have seen before, but now we don't get the data in the stream. We are having the entirety of our data. Okay, so that's the high level idea of the algorithm. And the only thing that's kind of left unspecified here is how do we construct these K random unit vectors, right? What can we do here? And the simplest thing we can do is to draw them from a random Gaussian distribution with certain mean and variance. That's the simplest way of just getting some random unit vectors. And again, you don't need to really implement here stuff. You can just use from scikit-learn Gaussian random projection. So you have that as given, and you can use that in your homework. I think you're actually asked to specifically use scikit-learn. And then another very frequent option for choosing random unit vectors is so-called sparse random projection. And here the idea is to construct these vectors such that you end up with very sparse vectors for your unit vectors UI. Here, there is a little bit vague because we have these special parameters S and density, but there is a version of this where basically you would have here, let me just maybe write it down. So I will give you some concrete numbers just to make the intuition behind this a little bit more concrete. So imagine that here you have as value 1/6, and here you have 1/6. And here this whole term is then 4/6, which is 2/3. And imagine that you are choosing here 1, and here -1, and here 0, and that you have some root of 3 in front of all of this. The way to interpret this with these concrete values is that you are rolling a dice, and if you get, let's say 1, you will here put into your vector value 1. If you had, let's say 6, you would put the value -0, and not -0, that's nothing, -1. And for any other values you get on by rolling your dice, you will put into your vector 0. So that means that that more often you are going to put zeros in your vector that you are going to put ones, because you are putting zeros with the probability 2/3, whereas for 1 and -1 you are using 1/6 as for the probability. So you will end up with something which is sparser. And that's good for making things more computationally efficient. And that's the reason people are doing this kind of construction of unit vectors opposed to just drawing them from the Gaussian distribution. Yeah, it makes the, as I said, downstream computations faster, and it also makes the storing of these unit vectors cheaper. So you get both storage and time efficiency. Okay, any questions about this? Okay, so as I said, you will just import Gaussian random projection or sparse random projection from scikit-learn. And that means that basically you are using this kind of algorithm where for unit vectors, you are constructing unit vectors by either drawing from Gaussian distribution or by constructing these sparse unit vectors by doing that case function. Okay, and that's basically it in terms of random projection. So let's just go over a little bit in terms of PCA SVD and random projection, what are the differences? So as we have just seen with random projection, the vectors we are projecting to are those that are randomly drawn from either Gaussian distribution, or we construct them by this sparse method. Unlike that, with PCA and SVD, we are choosing vectors that are those directions in our data where we have the most variance. So we are saying because there is a lot of variance in this direction, that direction must be important. Remember those illustrations where I was showing you when we have spread in this direction, when if we kind of collapse that, we will lose a lot of information, unlike if we had collapsed it in this direction where the data wasn't really spreading a lot, then we lost some information, but not much. The data was still on the line, which represented the structure of the original data. So the directions we are choosing, they are they either come, depending on how we calculate PCA, they either come from the eigen decomposition. So they are eigenvectors, or if we use SVD, there are these right or left singular vectors. In any case, they are way more meaningful than these randomly drawn vectors. They really represent what's important in the data. And that's why you will see when you think about, when people write about differences between PCA and random projection, they will say PCA preserves the global structure of the data, because you have considered what is important in your data, unlike with random projection, where you care about preserving these pairwise distances, and you are just projecting to the random vectors. So we are choosing widely different vectors here, and that choice has consequences. And it's not about, for me at least, which one of these is better. It really depends on what you want to do. If you really just care about preserving the distances, for example, you have a distance matrix, you have a matrix that represents distances, then having lower version of that, which still preserve distances, is enough. Okay, questions about that? Okay, that's clear. In terms of time complexity, we have seen that computing either eigen decomposition with something like LU decomposition or using SVD is not super efficient if we have a lot of features. So those methods are not super time efficient, unlike our random projection, where all we had to do is make a product between our matrices. So the complexity of this will be, so remember, A is n times D matrix, U is D times K matrix. So the complexity of this will be NDK. It's going to be linear in all of the dimensions we have, unlike with SVD. So this technique is way more time efficient. In terms of storing the data, we have seen that for SVD, you simply need to have your full matrix to be able to decompose it. Without the full matrix, it's not going to be possible. With random projection, we have seen that we can get the data as a stream, and that might be useful for some of your applications, similar to how we were dealing with streams of data when we talk about frequent items. The intuition is exactly the same here. Instead of getting just one numbers as in your stream, you are going to get vectors in your stream. And we are going to talk about this more in the rest of the lecture. Then, does it work for not super high dimensional data? Remember, when we talk about random projection, we have said that it all started from the lemma. So without the lemma, we didn't have anything. The lemma said for certain specific value of the dimension of the low dimensional space, you can get this guarantee. Without, if you had less features then you wouldn't get that guarantee, and applying that whole approach wouldn't make sense, because if your goal is to have distances preserved, but your lemma says, I'm not guaranteeing that for your values of K, then that doesn't make sense as a method to use. So if we look at random projection, it will not work well for data that's not very high dimensional. Remember the intuition I was giving you about why does this even work in high dimensional spaces. In very high dimensional spaces, random vectors are going to be almost orthogonal. Other ones in lower dimensional space, we don't have that property. Unlike random projection, PCA works well for we didn't have any constraints on the number of features we have. We just knew that there might be, that one feature might be predictive from the other one. We call this multicollinearity, and we wanted to get rid of that. So PCA, if you have small dimensional feature space, there is no, your original data has a not super huge number of features. PCA is a good method to use. Don't think about it just because we have introduced it first. It's a rubbish method, and these other ones are like more advanced versions of dimensionality reduction. It's not like that. They are really different methods, and I hope it kind of comes across that they have their unique properties. And as one property of PCA that we didn't like was the sensitivity to outliers, which came from the fact that we are minimizing the sum of squared errors. So if one of your distances between the original point and projected point was huge, then the model, the whole technique might kind of overcompensate for that one point, and then the other ones are kind of neglected and the whole thing is thrown out. I mean, if you don't have outliers, then this is not a concern for you. So PCA is, again, a good thing. Random projection doesn't have sensitivity to outliers because it tries to preserve the distances. So it's going to preserve the distances of the points, no matter where they are in your data. It's going to take care of all of them. And we kind of talked about this in terms of average case and worst case. We said for PCAs, we kind of worry about the average case, whereas with random projection, we are really focusing on the guaranteeing the pairwise distance preservation. So we are giving the worst case. Okay, any questions about all of this? Okay, that's good. I hope the lack of questions comes from clarity, not from confusion. Yeah, and just remember, again, I want to emphasize this, that these are different methods and they have, don't think about them as one is superior to other. Think about what fits your problem the best. Okay, so now I'm going to throw a little bit of equations at you because I want to introduce a new technique, and I was thinking how to kind of present it in terms of what we have seen so far. So let me go over methods we have seen so far and what we minimized with them. So with PCA, we were looking for a lower dimensional space, so let's call it F star, that had minimized the sum of squared errors. Remember, sum of the squared errors was, we are missing the square here. Sum of squared errors had taken for every point we had points from 1 to capital N, which is the size of our data. We have measured the distance between that original point and its projection to a lower dimensional space. And we summed all such differences and we wanted to minimize all of them. And then we have found, we have taken the product of each point with itself, not scalar product, rather the outer product, which gave us a matrix. We sum all those matrices to get what we call scatter or covariance matrix. Then we calculated the eigenproblem of that matrix, which gave us eigenvectors, and we have said we are going to take k eigenvectors, which were then k most prominent directions in our data, and we had to select k ourselves. So we needed to either do cross-validation, or we knew what k would be good for our problem. And important to that was that we had to center the data as well. Don't forget that. Then we have moved to SVD, and from SVD we have derived best rank k approximation. That was the thing where we took first k columns of matrix U, then we took the first k singular values and first k rows of the matrix V transpose, and we multiplied them together to get the matrix AK, which again was of the size of the original matrix, but that matrix AK had a rank of K. So it is the best rank K matrix that approximates A. And by approximation, we took the difference between A and such matrix and took the norm of the difference. So this matrix AK is minimizing such norm across all matrices whose rank is K. Here, minimization of this norm can be, I use C as a placeholder. It can be 2 norm or Frobenius norm of a matrix. And then finally, with random projection, we have focused on something different. We were looking for a subspace F, which again has dimension of K, such that for every points AI, AJ, when we take their difference in the projected space, projected to this k-dimensional space F, and their original difference, the difference in the original space, these two things had to be similar, approximately the same. I used a little bit simpler way of writing this. Remember, the lemma gave you that bounds with y minus epsilon and 1 plus epsilon on the two sides. It's just a more precise way of saying that these two things are approximately the same. All right, so now today we are moving to something slightly different. So we have introduced best rank K approximation, but we didn't talk about low rank approximation, which is slightly different. So low rank approximation is a matrix B, which is now not it's not in the same size as the original matrix. Here we have matrix of the size L times D, where L is lower than N. So think about your original matrices had N rows, now we are decreasing those rows to a smaller value. But this row space of B will contain a rank K projection matrix, PB. And when you use that projection and project matrix A with it, you are going to get something that's close to the best rank approximation. So let me read this again. We are looking for a matrix which has a smaller number of rows than our original matrix. That matrix will in its row contain a projection that you can use to project matrix to a lower dimensional space, and that projection matrix will have rank K. And if you project your matrix, data matrix with that projection, you are going to get approximation of your original matrix that's similar to what you would get with the best rank approximation. Okay, and this is going to be important for frequent directions, where we are looking for, basically it's a little bit confusing because in 2013, the frequent directions was introduced for the first time, to the best of my knowledge. And it was introduced as a way to approximate matrix efficiently. And the way to measure whether you have approximated a matrix efficiently is to say that, well, if you have found such matrix B, its covariance, B times B transpose minus A times A transpose, which is covariance matrix of A, should be small. And this is a way of writing that it is small. So you can say, well, I have found a matrix B that has less rows, but it is a good replacement for my original matrix A. And if you use this goal, it's called matrix sketching, where you're looking for a sketch of the matrix which it's smaller in the size and can be a good replacement for your original matrix. And if you look at the original work where they have used this bound, this was their goal. So it's called Simple and Deterministic Matrix Sketching from Ido Liberti, published in KDD 2013. Then the author says, well, what is the connection of this algorithm, which we haven't introduced yet, so bear with me. They will say, it is difficult to compare our algorithm to the line of work that do low rank approximation of matrices, since the types of bounds obtained are qualitatively different. So basically they are saying what we are trying to achieve, the kind of bound where we are trying to make the difference between those covariances matrix small is not really the bound that lower approximations are all about, which I hope is somewhat clear for how this bound looks and how this one looks. But they say, we note, however, that it is possible to use frequent directions to produce a low approximation result. So they're saying, we are kind of looking at different bounds because our goal is different. But if you are wondering whether this is tied to low rank approximation techniques, yeah, it's kind of connected, but it's not the purpose of what we are trying to do. So that was 2013. In 2015, there is, I think, almost the same sounding paper, where one of the authors is again the author of the previous one, where they say we are introducing frequent directions which can minimize two bounds. One of them is the one which we have seen in 2013 version of this paper, a little bit tighter than what was introduced in 2013. But not only that, it can also give us low rank approximation. So I don't know what exactly had happened here. Maybe we can ask Jeff, but I suppose they have kind of talked together and make this version of this paper, which is stronger and shows that it can serve two purposes, not only to sketch the matrix, but also to bring the low rank approximation. Okay, so yeah. let's go back to the bounds. Yeah. Yeah, I actually put them on the in this presentation as well. Basically, so this frequent direction methods is we will see it's very nice. It has these nice properties. It's not as canonical as PCA or SVD. So it's not like it's going to be covered in every single curriculum that is covering dimensionality reduction, unlike those that have, including random projection, that have scikit-learn implementation. This won't be implemented in scikit-learn.
Can you explain what sketching is again? I'm so confused.
Yeah, let me just finish this stuff. So I was saying that unlike these other ones which are more standard, this one is newer and it won't have standard implementation in scikit-learn. I guess the part of it being included is that, as you have noticed, that Jeff has been one of the authors of the frequent direction. So I don't really know all ins and outs of these methods. It's kind of new to me as well. So I put this paper and Jeff notes at the end of this presentation, where I will invite you to read a little bit more instead of me trying to wing it and say what is happening over there. Metric sketching. Metric sketching. So the goal of metric sketching is to find a matrix B that is has less rows than your original matrix. So notice that our original matrix is size n times d, but your matrix B, your sketch, is of the size L times d, where L is smaller than n. And when you read the definition of matrix sketching, it's going to be a little bit vague intentionally, because there are different ways to go about finding the sketch. And the definition will say something along the lines, we are looking for a smaller matrix B that we can compute efficiently, such that that matrix B can be used as a replacement for our matrix A. And now, whatever algorithm you want to use later on my original matrix, if your matrix B is a good replacement for it, you can just use matrix B. So you will see sometimes people will just write, we want B to be approximately as A, or they will say another way of kind of defining that they are very similar and that one can be used in place of the other is to say that the covariance, so B times B transpose, is similar to A times A transpose. So that's what you're going to see. And in the paper I have just shown you from 2013 KTT, I had used the definition where these two things should be, the covariances should be similar. So if you're saying they should be very close to each other, as always, we are going to take their difference and the norm of the difference to measure that. And you want to bound it by something. And here they are using the bound that's again, based on what's the difference between A and its best approximation. So yeah, you will see matrix sketching with the first line here. And then what we have here, you see it's very similar to this one, and it's very similar because it says this matrix B is a low rank approximation of A. Yeah, and then you can think, well, is SVD matrix sketching and best rank K approximation? And I would say yes, because you have found a matrix AK that's a great replacement for your original matrix. Yeah.
So is it just less rows, or is it like less features?
Here is less rows.
But if you were doing like PCA or SVD, wouldn't it be like less dimensions or features?
Yeah, it's different.
So
yeah.
that's kind of the difference, like the rows versus the.
Yeah, I wouldn't say so, because what you end up here with these as these rows are representations of important directions in the data. So we will see now when we go into this algorithm in this matrix B, each row will represent important direction. And when you go back to PCA and SVD and think about the right singular vectors, they were also D-dimensional, and they were also important directions. So I believe there is a connection over here as well. Yeah. So it's not like you have reduced the rows, but that's not to say that you have reduced the number of data points in your input. Yeah, that's as much as I can offer. I don't want to speak more because I think I will confuse you and myself. As I said, this technique is kind of new to me as well. Okay, so let's get into frequent directions. And I want to also emphasize that when you read about matrix sketching and frequent directions, one of the motivations is also going to be that you want to get this data as a stream. So memory here is also a thing to consider. So remember, with PCA SVD, best rank K approximation with SVD, we needed a full matrix with random projection. We don't need a full matrix to actually execute the algorithm, and the same thing is going to be true for frequent directions. So if you have a problem where you can't store your data, there is too much data coming and coming and coming, you will need to kind of go back and see whether your algorithm assumes you need to store the entirety of the data locally. Okay, so frequent directions, I don't know whether you guessed, because it said frequent, that we might have something to do with frequent items and one of the algorithms we have seen there, but it is actually derived from frequent items, that is Misra-Gries algorithm. So let's remind ourselves a little bit of what Misra-Gries was doing. Remember, we had our stream of data, and there we have our stream of data were just points or integers. We didn't talk about them in terms of them being vectors. If we had considered them to be vectors, we have said, well, we're just indexing them, and now we are working with the stream of integers. We have two vectors. One was counting items. The other one was remembering which items were important. Then for every item in a stream, we had done following checks. First check we have done is whether there exists an element in our location array that matches this item. And if we have found such item, we had increased the counter for 1. Then, more importantly, for our algorithm we are going to introduce right now, is what had happened if we did not have such element. So here, if we didn't have element in the array, but the full array was full, then we would decrease every single counter by 1, right? If there was an element, if there wasn't an element, but there was a 0, then we had placed that element into our location array and set the counter to 1. So these 2 points are important, that if there was a 0 in the counter, that meant, oh, we have a place to put this thing inside our location. So we did that. But if our location array was full, then what we did is decrease the count of every single element by 1. And then from there, remember, we had those bounds. So we could bound the true frequency. So if you had calculated certain frequency, or if you had estimated using this algorithm frequency of your element, you could have then calculate using these bounds the range of your true frequencies, because they were bounded by the estimated frequency plus m over k, where m was the size of your stream and k was the number of counters. Okay, so that was Misra-Gries, and the frequent redirections kind of follows the similar steps. So let's go over this. We won't have counter and location array. Rather, we will have just something which more resembles location array. And then in those locations, we will try to remember what were the important directions in our data. If we can't put a new direction in our metrics, we are kind of going to emulate that process of decreasing the counters such that we can get to 0 and then we can put the new one. It's not going to work exactly like that, but that's the intuition to what were frequent items there for us are important directions in our data. And we are going to exploit those to if conditions. If there is a 0, I'm placing my new element. So here, if we have some kinds of zeros, we are going to place our new direction. If there are no places to put our new directions, we are going to do something that simulates decreasing the counters to be able to eventually place a new directions. When we decrease so much, we had zeros in our counters. All right, so let's go over that. So we will have as our step 1, we are going to initialize. Okay, I'm going to write with capital letters. Step 1. Initialize matrix B, which will be element of L times D with zeros. For now, don't focus on what L, ignore what L is. It's going to again be connected, remember, in lots of algorithms we are choosing, some of them the size will be just a hyperparameter we need to figure out from the data. Here it's going to be more tied to the bounds we want to give. So you will get some, it will give some epsilons, and from those epsilons you can again set the L. So just ignore this for now. And then we are going to do the same thing we have done with Misra-Gries. That's for every element, for every data point we have, we are going to do something. And now our points are not one real value, they are the dimensional vectors. That's a difference from what we had before. And this is basically row in our data matrix A. Okay. So if we have, as in Misra-Gries, I will call this step 3. If there is a 0 row in B, then you're going to replace 0 row with your element AI. That's the same as in Misra-Gries, when we had 0 in our counter, we had placed the element in the location array. Then, I don't know why I'm writing these steps, but now I'm too invested. If we do not have 0 row in B, we need to do something different. And this is the same as if we have now filled our location array in Misra-Gries, and we don't have, we want to place it into our location array, but we can't do that. It's full. Now we need to decrease the counters to eventually be able to do that. So we are kind of doing that. So our step 4A is going to do SVD decomposition of the matrix B. And there are, of course, immediately might come to your mind, well, wow, we have now, again, use SVD, isn't it inefficient? it is not super efficient, right? But we have lower dimensional matrix B here, L times D. And so this won't be as expensive as it might seem initially. So SVD general is expensive if your dimensions are huge, but here it won't be a huge problem. Especially because this also won't happen in every step. So we are not doing SVD all the time, so the amortized cost will be lower. All right, so step 4B says now to define a value, delta I, to be your squared L singular value. So this is L singular value squared. Oh my God, squared. I don't know how to spell this. And this value is basically in Misra-Gries, we were decreasing by 1. And here you can think about delta I as how much are you decreasing the counter. It's not 1, but delta I. You can kind of think about it in that way. Yeah.
Can you repeat step 4B?
Step 4B, yeah. So this is ugly delta I. So it is a value we are defining, and it's going to be set to the value of sigma L square. Sigma L is L singular value, and singular values come from here, because we have done SVD decomposition in the previous steps. So these two things are, this is where you get your L singular value. Is that clear? Great. All right, and then in step 4C, we are going to do something that kind of goes into decreasing each one of the counters. It won't be exactly like that, but the intuition is similar. So we are going to define a matrix S prime. It's going to be a diagonal matrix. Okay, and remember, whenever we are defining diagonal matrix, we are just defining it by the vector of values that's going to be on diagonal. So on diagonal, we are going to have a square root of singular value, first singular value squared minus delta I. And we are going to do that for each one of the singular values. So we'll have L minus 1 square minus delta 1. And then if we now put the last one, sigma L square minus delta I, because delta I has been defined by saying it's sigma L square, this term here is always going to be 0. Why is this important? So remember when we talk about Misra-Gries, and then we said we are going to put K counters, but we are actually then filling K minus 1 counters. Remember, there was always a confusion between K minus 1 and K. What was implicit there is that one of those counters will always be set to 0, and that has some implications on the calculations in the math. So this is happening here as well. Basically, you're forcing that one of your directions is always a 0 direction. So if you're doing this exists 0 row in B, this thing will be ignored, I believe. Okay. Another thing you can notice from how we have defined this is that we are always subtracting the same value from each one of these. So we are always subtracting delta I. And this is important because in Misra-Gries, we have always decreased exactly 1 from each one of the counters. And this is a similar kind of behavior. We are from each one of the important directions, we are going to decrease exactly the same amount of like mass. So the fact that we are decreasing delta I from each one of them is important. And another thing you can notice is that because when we do SVD decomposition, from SVD, we get from a matrix of singular values, right? Sigma 1 to sigma, let's say L here, all the ones, everything here is 0. We put this singular value such that sigma 1 is the largest, right? Sigma 2 and sigma L, which is larger or equals to 0. So what this means is that these values are also in a decreasing order. So try to remember that as well. Then the final thing we do is step, I guess 5 or D maybe, is calculating new B, which will be a product of S prime times V transpose. V transpose comes from, again, singular value decomposition. Okay, so this is now important. Obviously, because it was one of the steps, but not only because of that. So we have from our SVD calculated vectors, right singular vectors. And we remember from what we have learned about the SVD is that these vectors represent important directions in our data, right? So these are important directions in your smaller representation of the matrix A. Now, each one of these directions, you are going to kind of demote a little bit, just like you did in Misra-Gries by demoting, decreasing the counters by 1. You are effectively doing the similar thing. Here, you will demote those important directions by multiplying it with this matrix S prime, which has these, each one of these singular vectors, which was initially tied to the importance of that corresponding vector in the matrix VT, it will demote it a little bit by this delta I. Okay, it's a little bit mind bending, so I want to stop here and try to answer your questions. I'm not sure I can answer all of them, but is the at least general idea and connection to Misra-Gries somewhat clear? Yeah.
So if you use like, if you have like a lot of like data points, so it's a point where like you drive from the matrix, like all the data points, so you have to approximate more than them.
Yeah. Yeah, so you're right. You are having lots of data points. They are coming again into as a stream of data. You don't want to store them into as one gigantic matrix, or you even don't have that capability because the new data is constantly coming. You would use something like this, and then B would represent important directions in that data, but it will be computed dynamically instead of like with SVD. We would have to store all the data, then compute SVD. We would get those important directions from the matrix V transpose, but we had assumed we have put everything on locally first, and also we're not worried about time for complexity together with the storage.
Yeah, I guess you use like that, just some dimension SVD. It's something that like say one of the dimensions that you would have like an L by N, L by K like maintenance. That would like I would or something like that.
Yeah, with PCA as well, we have computed the important directions, and then we had remember that illustration. Basically, when we found important directions, that was a situation when we had two features. One of them was actually important, the other one was rubbish. And we had kind of projected the original points to that line. So that line was lower dimensional representation of the original data point. It still lies in a 2D space. So when you visualize it, it's still, you have 2D points that you are visualizing, but the rank of the data is 1, right? You have one, like just a line that represents them. Which is a little bit, I think that's where things can be confusing if you're just hyper focusing on what are the dimensions, because at the end you can get the same dimensional matrix, which has a structure that's obviously slightly different. Like we didn't have those variants in this direction, we just have the variants in that direction, because we are focusing on important directions. All right, any other questions about this?
Like clustering in a way, clustering is like part effectively. Where this is like completely like different like elements. Like how they
I don't think it's clustering, because in the end you can get a lower dimensional representation, but you don't know where each, that one set of points is part of one cluster versus the other one is not. What these techniques, how they are connected to clustering, is usually people do this low rank approximation of original data, and then they apply clustering technique using the lower dimensional vectors.
This method is for reducing the number of rows that you have. Right?
Again, effectively you are doing that. So you are getting a matrix which has less rows.
So,
But those rows now represent important directions in the data. So what you're getting in this matrix B is, I believe, what you would get with singular value decomposition and matrix V transpose. Those are important directions in your data.
What is the difference between an important direction and an important feature? Like,
So, yeah, that's a great point. You will read that PCA is not a feature selection method, which means that it doesn't give you important feature. It just removes features that are predictive from other features. So in your columns, you might have a feature that is very easily predictable from the other feature. I think classical examples are someone's income in a certain job and their age or something like that. So basically, you don't need that feature from the problem at hand. So you kind of remove those features from your feature space because they are not super useful for you to do whatever data analysis you have after that. I think it's easy to then say, well, then those are important. But people are very strongly opinion to say that those are not then, that's not a feature selection method, rather just removing noise or removing something that's redundant from the data. I don't really know how to explain the difference between two. I just can offer that perspective from the literature. Yeah.
what is the direction?
Well, remember, like in those illustrations, so you had your data that was, let me maybe add here, add page. Okay, so remember I was showing you data points that look something like this, right? And then we said important direction for something like this is going to be, if you had, it's going to be something like this, right? Because here you have a ton of variance in your data. And if you had collapsed these points here, if you collapse the second dimension, they would all end up on this line, but that line or tells you a lot about the structure of the data because data is spread in this direction. Whereas in this direction, if you had collapsed data in this direction, you will get some kind of blob that's in a center here, which doesn't resonate with how the data looks like, right? That it's spread like this. So important direction here is kind of telling you where do you have the most variance in your data. So when you get that vector that represents that direction, it's not interpretable, right? Because it's just the direction.
So would the direction then be like the points that are leading to the feature that like?
I think the best way to think about it is direction of the data where you have a lot of variance, where data, see the data points here and data points here, they are like really differ. Whereas points that are over here, they don't differ time.
So like the points that are really close together, those are like ones that you would be eliminating because they aren't serving like the range of the variance?
Yeah, I wouldn't use distance here to say, I'd really say variance because you're looking at the variance across the direction. So these points two here are close together and that's not relevant, right? So it's not about the distances, it's about really where do you have that a large spread of the data versus where you don't have data that spreads a lot across all the points of the data. So it's in that sense, it's global. And that's what people emphasize about PCA, that you are looking at these global properties of the data, namely where is the spread large across the entirety of the data and where it's not large. So if 2 points are close to each other, that really doesn't tell us about the importances. Yeah.
That makes sense. Thank you.
Okay, good. Okay, so this is just repeated what I, oh, sorry, yeah.
Sorry, but, so I had a question about, delta I. So, in step 4C, it says that S prime is, diagonal, where, every I, let's say every L element of the diagonal is, sigma, the L singular value minus delta I. What does the I and delta I represent? Like, is it just a
Oh, for every single point here, for every AI, you are going to do this procedure. So
for every row?
yeah, exactly. So in the next row, if you still can't find a zero row B, row in B, you would do this again, but you would use different delta I. Yeah, so that's where I comes from. Yep. Yeah, and that's all that is connected. And here I will invite you to read more about that in Jeff's notes. Where am I? Here. All right, so here in Jeff's notes, you can find more technical description of how that delta I is increasing the mass of the direction. I don't want to go into that because I'm really not confident I can reproduce what's written here in a more explainable way. But the delta I's are connected to the how much are we decreasing the mass and influence of each one of these each one of these vectors we get from the SVD. So yeah, definitely read this to get more precise way of explaining what decreasing a mass of that direction means. Okay. So that's basically it. One thing I didn't say is that in the end, when we are done with all of this, we are just going to return our matrix B, whatever we get at the end, just like we had returned the location array in Misra-Gries. Okay, this is just what I've said repeated, and this is how the algorithm looks like when we write it in a whatever professional form, I guess, which is the same thing we have written over there. Okay, and now there is like a lot to say about analysis, and so I will leave for you to read more about some of the stuff here that are relevant, such as why do we use the SVD. I think it's important to get those important directions, and that's exactly what SVD will get us. But also this delta I is connected to certain norms, and those norms are related to SVD. This is a math I don't want to work out here, but using delta I to be defined as a singular value squared has a connection with the norms and how much we are decreasing the norm of each one of these singular directions we are taking. Again, this is something I have mentioned before. Do we need to use the SVD? It's not as terrible as it seems, because the complexity is DL squared, but the total cost is NDL, because we are not doing this SVD every single time. We are doing it when we need it. And yeah, there is, maybe you didn't ask this, but it might have been maybe slightly confusing to you. Why have we defined here B as the product of singular matrix with the right singular vectors, but we didn't use left singular vectors. And if you remember, when I was explaining SVD to you, we have kind of derived all the steps of what happens when you first use V transpose. You are rotating your coordinates. Then with S, you are scaling them. And with A, you are kind of rotating back to the original space. And that second rotation is not really needed, because all we care are important directions and how important they are, which is given by singular matrix. So we don't need to go all the back to the original space. And that's basically what is written over here as well. Okay, so that's all I want to say about frequent directions. I'm also inviting you to read not only the notes, which are written by Jeff, who had invented the algorithm, but also their paper that I have shown you briefly. And here you can find the derivations for those bounds if you are really interested in knowing more about that. So definitely read that. As I said, there isn't a standard scikit-learn implementation of frequent directions, because it's not as standard of the algorithm, at least yet, as a PCA random projection and SVD are, but they have code base. The authors has released their code base, so it's definitely a great place to start if you would, for example, use these frequent directions for your projects, let's say. Okay, since we have a few minutes left, I just want to show you one more thing about random projections. So, yeah, remember when we came back from the spring break, we were talking a little bit about kind of what is the place of these techniques in the real world. And I told you that in many and almost all cases, it's not that you're going to use, let's say, clustering as your final solution. Rather, that will be like one step in your pipeline. And then having better cluster data, you might do something better downstream with it. And I want to use this paper as an example of that. So this paper called Linformer, Self-Attention with Linear Complexity, takes one of these very important neural network architectures called transformers that we all use today for all sorts of applications. It started all with textual data, but now we use it for vision. So there is vision transformer. And if you have heard about AlphaFold, for example, where DeepMind had developed a model that can find new proteins is also based on transformer architecture. So it's like a main component of a lot of deep learning techniques and methods and models we are using these days. It's an absolute must if you are if you are working in any kinds of applications that deal with text these days, if you use deep learning. And one thing that this paper had observed is that if you look at, so I won't explain to you what transformer is, but you can imagine that there are a bunch of matrices inside transformer, and that this collection of matrices in a sequence makes up the model, like any other neural network architecture, if we, simplify it a lot. So here they have calculated the rank of each one of the, excuse me, not the rank, but they have measured how many eigenvalues we are going to see out of all of them if we are at the index 128. So if we have seen 128 eigenvalues, we have seen 90% of them. And that means that the rank of these matrices, the full rank would be 512. They are actually with the low rank approximation. Let's say if you take rank of 128, you most likely can get a good low rank approximation of the full metrics inside this model. So first, what they did here is to show that these matrices are low rank. And then from there, they have said, well, okay, if we can, if these matrices are low rank, let's just use a low rank representation of these matrices instead of them to be able to have faster computations out of these models. They first used SVD, but then they found, oh no, SVD is slow and we don't really want to use it. So what they did is they find the something called linear self-attention. And when you look at how they did that, well, they used our Johnson-Linderstrauss lemma. And from there, they could, with the techniques we have seen, they can define a new way of defining these matrices, which made everything more efficient. So ins and outs of this, you won't know if you have never seen transformer especially. But the point here is that the most important architecture we are using in machine learning and AI, or whatever brand you are liking, is transformer. And transformer, by using this technique we have learned in this class, you can recognize, okay, whether these matrices are low rank or not. If I can approximate them with something which is of smaller rank, how would I go about this? And you can recognize that if you do that, it can give you benefits such as time efficiencies of these models. So yeah, it's not like in the end you are going to that's going to be your final solution, but it was one step in your modeling approach that had given you great benefits. And that's kind of how I want you to think about these techniques you are learning about as tools you have that can enable you to have better modeling approaches later on, not as the final solutions. Okay, I hope that's all I wanted to show. Let me just check. I don't have any other slide. All right, I don't. I will need to skip today's office hours. So if you need me before office hours on Wednesday, please let me know and we can arrange something if it's urgent. But TAs will be there. So if you have questions about homework, it's Monday, yeah, homework, then yeah, you can go there. Right, see you on Wednesday.